So if X is a smooth projective variety, everything is over complex numbers, then so in the basically going along the lines which I mentioned yesterday, we can give a map from codimension C cycles to H2C X Z. Okay. So note that this is weight 0, and of course you should have weight 0, and or more generally, if you are looking at X cross Y, X and Y smooth. So yesterday I said this only for the graph, but more generally, if you have a cycle on X cross Y, then you can produce a map H n minus 2C X Z. So minus C. I got the sign wrong. M plus 2D. No. Okay, I'll check it in the notes, but it's one of these. Okay. And the idea is, of course, as usual, to write this as a linear combination of subvarieties, and then you have so that will actually clarify whether it's plus or minus. So you have of course you have a map from HM of X Z to. So you'll see that now we are not assuming that VIs are smooth. So the intermediate, as Srinivas remarked yesterday, even though these endpoints are pure Hodge structures, the intermediates are not pure Hodge structures. The intermediates are mixed Hodge structures, right? So you have HM. So you just take the first projection restricted to V, and so you get HM of Z, right? And then you also have HM of VZ to H. So it should be, so 2 plus is correct. Okay, except that there's a twist, and the twist is because we are going to use the intermediate step of putting it inside the normal cone. And then use the fact that this is isomorphic, right? So then you have M plus 2C X cross Y minus V Z C. Of course, there's a natural map in cohomology to X cross Y. M plus 2C ZC. Right? And then finally, we talked about this yesterday, that you can HM of x cross y z, you have to HM H2D, if x is of dimension d, H2D z cross H n minus 2D y. Right? And then this is going to give you a z minus d here, and so that gives me this factor. So this is the composite map, and then you take linear combinations and you will get a map which is a map of pure Hertz structures. Okay, but the intermediate steps require you to say that it is actually a map of mixed Hertz structures. You will have to say this is a mixed Hertz structure, this is a map of mixed Hertz structures. This one is pure, but the map is of mixed Hertz structures, and so on, and you will get a map. Okay, so you can see that in some sense, in order to talk about things to do with cycles, there is no way of avoiding mixed Hertz structures. But I want to give another important example of this kind. So take the specific case where you replace x by curve of genus 1. Okay, and the cycle I'm going to look at is two distinct points on points. Okay. And if you do this similar stuff, you will write your standard exact sequence H2P of Hk of E relative to E minus PQ, Z goes to Hk of E, Z goes to Hk of E minus PQ, Z goes to Hk plus 1 of E relative to E minus P Z. And again, we'll use the usual deformation to normal cone to say that E minus PQ Z is Hk of, in this case the normal cone is just A1, so Hk of A1 minus a point and two copies of that. Okay. And we know what this is, right? I mean, this is the simplest possible thing. It is 0 if except when k is equal to 2. And when k is equal to 2, our usual computation will say that this is z. If I got it right, it should be z minus 1, because it's weight 2. Okay, so this sequence here gives me a short exact sequence H1 Z to H2 of E minus PQ Z to Z1 Z minus 1. H1, sorry. Yeah? And, oh sorry, I should have said something before saying this. Yeah. Instead of putting this, goes to kernel of Z minus 1 direct sum 2, that is this term here, H2 term, and then the next term going to H2 of Ez. Right? That's the correct thing. And then it's surjective. So kernel, big bracket if you like. Right. But of course, if I have distinct points, certainly the term is going to 0. Right? So the difference between the 2 points is going to 0. So if you take 1 minus 1, this goes to 0. So you could equally well write here z minus 1, and symbolically we can write p minus q. Okay. So here you have a mixed charge structure, and somehow this mixed charge structure is clearly going to be something which talks about the difference between the 2 points on an elliptic curve, and from algebraic geometry we know that this is sometimes 0 and sometimes non-zero, right? I mean, certainly on an elliptic curve, if there are distinct points, it's always non-zero, but yeah, so in a general curve it may or may not be, yeah, so, right? So, I mean, nothing special about an elliptic curve here except to say that if p is not equal to q, then this is non-zero. This, then we know that somehow we should think of p minus q in the Chow group of codimension 1 of E is non-zero, right? Because there's no function which is this, and if you, well, so so mixed charge structures appear in terms of, so you can think of this. So remember that mixed charge structures, we said it forms an abelian category, and this can be seen as an extension right. So even though we are looking at smooth varieties, somehow when you are trying to study cycles, mixed charge structures appear via X groups. Okay, maybe this kind of answers one question which Nitin asked yesterday, that can we detect things which are not homologically trivial? Well, in the context of mixed charge, cycles which are homologically trivial. So I rubbed this out, but we had a map from cycles to cycle classes. And of course, if a cycle gives you something which is homologically trivial, it's not detected here. But here is a cycle which is homologically trivial, which is somehow detected by some mixed charge structure, provided, of course, we say that this extension is non-trivial, okay, as mixed charge structures, which is okay. So we want to have a notion of taking mixed charge structures, and so first of all, therefore, we need to say what is in general, what is a cohomology theory, and with values, so in some abelian category, but ultimately with values in mixed charge structures is what we are going to look at, right? And what does this mean? It simply means that given any pair x, y, and some integer I should associate a group hi, x, y, z, and maybe if you want to throw in the twist, you can throw in the twist, but that will come more or less automatically when you product with things like h2x, right? So you don't have to worry too much about it. And such that we have, if you have a map of varieties, then you should get a map of cohomologies in the opposite direction, and so on. And the last important property is the boundary map for the X triple. I think I wrote this in the first lecture, but maybe I've forgotten now. Is associated with a map X contains Y contains Z, right? So, I mean, this notation simply means Y is contained in X. These are varieties and so on. And this is Z contained in Y is contained in X. Then you have the boundary map going from HI of YZ to HI plus 1. of xy. Unfortunately, there are two z's, but okay. Right? So you have this. This is what you would like from a cohomology theory, and the construction of Nori is to say that there is such a universal theory with values in a certain category. So there is kind of some other category which he calls effective cohomological motives, which actually sits over, in some sense, the category of mixed thought structures, and where maps are coming from this in some fashion, right? And you have a theory. So effective, this is called effective cohomological. Okay. And you do have a theory with values in this. Now, one could ask, why do you want to do this? You already have mixed thought structures, and it seems to capture what you have. Okay, so the question is, why do we need something which, I mean, maybe this is an equality, right? So do we have any reason to believe that this is not the same as this? Okay, and the reason, at least one reason, comes from the fact that not everything occurs in this fashion. Okay, so, and I suppose the oldest such example is that of Mumford-Reutemann. Okay. So just go to the next higher dimension, and what they construct is something which is a non-trivial cycle, P minus Q, cycle on a surface like a K3 surface, let's say abelian surface or K3 surface. Okay. So if I have such a cycle, then, I mean, as such, you could try to do something similar to this, but that's not going to get you very far, because there's no, I mean, this relative cohomologies will not be the right dimension. But you can show that if you, so you can put this in a curve, and then you can ask, take the extension class of the curve. Is that extension class, when I restrict to the cohomology of the surface, the natural map from the cohomology of the curve to the cohomology of the surface, is that class, does it remain non-trivial? And the statement is that it splits for every curve. Take any curve, right, and look at the corresponding class in the Jacobian of the curve, right? Then that sequence, even though the class is non-trivial, the sequence splits in that setup. Okay, so the image of that sequence is split. So in some sense, let me just.
In K3 surface case, the sequence will be H3 going to H3 is the open. The H3 of the K3 surface is 0.
Right.
Of course, an extension otherwise 0 is split.
Yeah. Okay. That's a good way to see it. Yeah. So K3 surface is easier to see. H3 of the K3 surface is 0. Right.
Kapil, a naive question. When one studies the knowledge what you are doing,
right.
So now among those actions is a kind of normalization that for a point it has to be zero.
That's right.
But no inertial properties is demanded.
Mm-hmm.
Here you are not normalized, but you want the inertial property.
Well, normalized is.
Can you instead normalize and then inertial property automatically?
I mean, in some sense, the fact that we are lifting the existing theory says that all those things are already, that is already a normalization. right? Because we are not saying that it's created from nothing.
But then once there is this normalization, does it automatically have universal property, or among all such you won't have something like this?
No, among all such there's a universal property, but there is some base change theorem also. I mean, maybe that's what you are asking. Change something like universal coefficient is possible. Yeah.
In topology, you also say suspension as isonormal. There's nothing like that here. Not isonormal. There's no suspension. There's no cell structure. That's how topology will reduce the root to point. Yeah, that's why point you build up things.
So the close. I'll say something about the cell structure part. I mean, because the basic lemma says that there is a kind of cell structure which does this construction, but the problem is we'll see. Okay, so there is there is such a class which is a non-trivial cycle. Okay, but your H1 elements, the X1 elements don't detect it. Okay, that suggests that you should have something which has an X2. Okay, but this one doesn't have an X2. So that's the problem. There's nothing to detect the given cycle. So you would want to say, therefore, there's some kind of a refined. Also, we saw yesterday, or I mentioned yesterday, that there are Hodge structures which don't come from varieties at all, right? So you do need to refine this category somehow, and so the idea is somehow to use some kind of a universal construction, as Nitin said, to construct this, and basically the idea of Nori is something which he calls basic lemma. Okay, which says that given x, z, there exists something in between x and y, there exists some z in between. Okay, and I should have said, assuming dimension of x equal to n, there exists something in between such that Hn, Hi of x, y, z is 0 for I not equal to n, and is a free abelian group something for I equal to n. Okay.
Not with y.
Oh, with z. Yeah, I mean, that would be. Yeah, you don't know what it is. Note that since this is a pair, this is a mixed Hodge structure. I'm not saying that this is some pure direct sum of Zns or anything like that. This is a mixed Hodge structure. Okay. And then basically this gives a kind of cell complex structure, right? So what you have done is you have taken an x comma z, you have put something in the middle. Now you can call this as z as x1, and then between x1 and y you can put something, okay, and so on. I should have said that z is properly contained in x, right, and does not contain the generic points of x. Okay, so it's strictly of lower dimension. It's like a divisor. And so it's of dimension 1 less. I should have said that, yeah. Okay. So now you can filter the space, and which is exactly like a cell complex structure, except that it's done in the algebraic geometry sense, and you can use it to calculate the HIs, provided these. X is a variety. Yeah. Right. Irreducible variety. Okay. So the problem is that there doesn't seem to be, other than saying this condition, there doesn't seem to be a direct way to identify such varieties. Okay. Whereas in in your classical topology, you can say, well, it's a cell, it's a single cell, or it's you can represent it by a cell complex where there are only x consists of cells of dimension n attached to a complex whose dimension is n minus 1. But as such, there's no, other than saying this, I mean, topologically, you would like to have an algebra-geometric way of identifying such pairs xz, but that doesn't seem to be so straightforward. Okay. So what you would like is to say that using this, you write, as I said, you can write x1 contains x1, sorry, not contains, but x1, x2, and so on. Just repeat the process until you get to x, whatever, suitable. You're going down by n dimensions, and then you'll get y, but which is y, right? So something like that.
The formulation of the pairs,
right.
is any closed subset.
Y is a closed subscheme, yeah. So we need, so we can, in general, we can, of course, we can talk about arbitrary pairs, but for the purposes of the lemma, it's a closed subvariety. I should have said that. Actually, you may as well assume x is affine, because you're going to, in some sense, you're going to throw out what is in y, right? But okay, taking cohomology of the pair. So, but the idea is that now all cohomology is written as the cohomology associated with a complex of such spaces, the mixed Schwarz structures associated, right? So once you have written something like this, you can use the boundary terms to write a complex Hn x1 goes to h, it should be, I'm getting it in the wrong direction. What is going wrong? Hn plus 1. No, obviously it's in the other direction. The boundary map is in this direction. Hn minus 1, x1, x2, and so on. So you get a complex of mixed Schwarz structures. Each of these is a mixed Schwarz structure. And the cohomology of k of xy, z is the complex, is the kth cohomology of this complex. Okay. So modulo, of course, the fact that there is no functoriality about the choice of this z, you can at least see that if I can put mixed Schwarz structures on these things, then on this kth cohomology I can put a mixed Schwarz structure. Okay, and then one would have to prove that it's independent of all the choices and things like that. Okay, so in some sense you can see this as one way of extending whatever we talked about on the first day, how to associate a mixed Schwarz structure to a variety. Okay. Anyway, so you can construct ultimately this category ECM based out of such pairs. Okay, so you have this category, and one can hope that it has all the higher X groups. Okay, so that's the hope. And so as I was saying, therefore the idea is that there are this is the hope, that there are higher X groups in this ECM. Okay. You should have X for, so let me say what the conjecture is, then it should be okay. So
in the MHS category, X2 onwards, everything is 0.
In MHS, X2 onwards is 0. So somehow the point is that by going to this refinement, the X2 onwards are not 0.
The formula is why X2 is 0. For MHS.
Why, you mean, why is X2 0? Yeah, are you asking? What is the simple reason for X2 being 0? Huh? No, yeah. So, I don't know, what is the simple
Well,
explanation?
one way is to argue when you write X1, the sequence. You have a short exact sequence, form something into it, write the long exact sequence.
Right.
The X1 to X1 will be certain.
Yeah. Yeah, I mean,
By direct competition.
yeah.
Because
Maybe.
you have tensor products and duals and the like.
I think I thought it has something to do with the fact that the Hodge structures are polarized, but maybe I'm wrong. Anyway, okay, I'll think about it, but okay, it will come back. Something to do with the fact that you are working with vector spaces, ordinary vector spaces, and anyway, yeah, so. Okay, so what is the conjecture about these higher X groups? It has to do with the fact that you can, so as I said, you are looking at the map from cycles of codimension C, X. So this gives, you can think of this as each such element gives an element in H2 C, X, Z, C. And so you can think of this as giving a homomorphism like this in ECM, right? And then what you would like is that the kernel of this, so let's call this C0, and then you should have a map from kernel of C0 to X1 ECM Z H2C minus 1 X Z C and so on. Okay. C1 X. So. Okay, and so on. So this is what you would expect. Okay. And of course, as Nitin says, one question could be at what level should the X case of ECM should be 0? There's also some conjecture about that. So what you would actually like, of course, is not only that this is true, but that the things which go to 0 under all these maps is rational equivalence. Okay, so that's...
So what is the C0?
C0 is the cycle class map which I talked about right at the beginning. Associated with every cycle on X, we produced an element here. So that's a map from cycles to this, right? And this one is more or less, you just follow what I did for elliptic curves and you will get a map, right? So, and so on. So there's a hope that you have such a filtration and extension. Okay, and that the kernel, so that is part of the statement that there are higher X groups is a way of saying that if you say that the kernel is rational equivalence, then certainly they have to be higher X groups. Because, because some element which you know goes to 0 and here does not go to 0 here, right? Because at least we know it's non-zero, so the kernel of all these maps has to be rational equivalence, means somewhere or the other it should be non-zero, right? So that means the higher X group should be there. Okay. Now, you might wonder that, okay, with so many conjectures, should we try to refine this further? But it is still interesting to refine this a little further. And the reason is that if you look back at the example of K3 surfaces, the other way it was proved that if a surface has H2 0 X equal to 0, okay. So note that the two examples I chose, the K3 surface and abelian surface, H20 is non-zero. Okay, so if H20 is 0, then at least many examples of surfaces were known where this kind of phenomenon does not happen. Okay, and that is so-called Bloch's conjecture. Is that H20 is equal to 0, then this X2 is 0. And there is no such class. In other words, the map from the Chow group of codimension 2 cycles on X to tensor Q to the whatever, to rational equivalence or this group. I don't know how to say this, to the combination of the integer cohomology and extended by, in some sense I'll write direct sum. It's not quite direct sum because you have to take the kernel of this plus Albanese, which is H1, which is the X1 group. This kernel is 0, has no kernel. And this was proved by Bloch, Cast-Lieberman in many cases. Okay. So it somehow it's governed only by H20, and the H11 part does not play a role. Okay. So it's not just this, but here I can actually, in this particular case, I should go mod H11 in H2. Right? So I should actually take H2x. That's the term which will appear here for a surface, right? C is equal to 2, so 2C minus 2 is 2. And so H2x Z1 divided by the Néron-Severi group of X is what appears. Okay, so it's, or if you like, perpendicular to the Néron-Severi group. And that is what should appear here. Okay, so, and this, so I'm saying this because Sudarshan asked this question, will I talk about Hodge theoretic connectivity? Okay, so this is an example of what you might say is Hodge theoretic connectivity, because it means that it's Hodge theoretically once H20 is 0. So if this is if this Néron-Severi X is perpendicular is 0, that means H20 is 0, right? So which means that it's Hodge theoretically of a smaller dimension. Everything in the H2 is coming from curves. Okay, so it's though the variety is a surface, but the H2 is like a curve. Okay, so when you have that phenomenon, then you say it's Hodge theoretically of a lower dimension, right? So more generally, one can go modulo, so you can talk about what is called the width of the Hodge structure. So you can look at H, N, X, C. Well, forget the C for the moment. And you can look at the Hn of some W, Z, where dimension of X minus dimension of W. So take a map, right? W to X. And suppose this is codimension C. And suppose there is a surjection. Or more generally, you can take the sum over all such things and take the image, and they can call that the width C part. Is not the weight, but width C. NC, I suppose, right? What is the terminology? NC of H N X C is the sum of all the images. And in some sense, we are claiming that the Hodge groups are governed by X. So since everything in this is tensor Q, I will go back to tensor Q. X, ECM, K, H, Z, H. Okay, so I'm going to get the numbers wrong here, I'm sure. 2C, minus 2 minus k x so, mod nk or nk. Okay, so the claim is that chow C of x has a filtration where the associated gradients are these groups. Okay, so this, you can say that this is the most most optimistic conjecture that we have about cycles in this context. Okay, and you can also, instead of writing this, I think in Janssen's book on K-theory, so there's a book by Janssen on K-theory where this is stated. At least that's where I saw it for the first time. But then he attributes it to Beilenson, and I don't know where in Beilenson it's published. So he will write it not like this, but in terms of the perpendicular of this inside that. So you can ask for examples of how would you go about doing something like, how do you expect to prove something like this? Okay, so the basic idea is which, I mean, is to decompose the diagonal into idempotence. So let me say what that means. So you have the class of the diagonal sitting inside Z d x cross x, right? And you want to decompose this into a sum of what I call pi i's 0 to 2d. Yeah, maybe this diagonal decomposition looks a little bit out of the hat, but perhaps the simplest way to, there's this work of Bloch and Srinivas which explains how you can use diagonal decompositions to do things. But even before that, the non-trivial classes were typically constructed using the diagonal, right? So you can even
standard conjecture correct components of the diagonal.
No, that's even older. That's Grothendieck
Topology.
topology, right? But the question is, why do you expect that diagonal decomposition will prove something like this? That's the question. I mean, you can conjecture that there is a diagonal decomposition from topology, but why would it prove something like this? So perhaps the idea goes back to the way in which this Reutemann result is proved, or even for elliptic curves, you take the diagonal in the elliptic curve and subtract p times the point, right? And then you look at this cycle, or maybe this minus e cross p, okay? And somehow this is the cycle which represents the non-trivial part of H1, right? This cycle will be what represents the H1 tensor H1, okay? So in any case, so the idea was that you can prove such a result if you can get what is called the Chow-Kuneth decomposition. So this is also in a work of Murray. So he has two papers, but the second one is mostly examples, so you can look at the first paper. I'll put it again in, I think it's called Decompositions of the Diagonal or something like that. Right. So what do we want about this diagonal decomposition? So you want to write it as a sum of pi i's, and pi i's should have the property that pi I square, pi I times pi j should be equal to 0 or pi j, right, if j is I is not equal to j. So it's an idempotent in the Chow group. Okay. And then you not only want to write the diagonal as a sum of these things, you want to write it such that its action on the appropriate cohomology group is 0. Right? So we said that in the beginning that if you have a decomposition of the cycle into a sum, so each of these cycles gives rise to a map from the cohomology of x to the cohomology of x, and it should be 0 on the hi, except on hi or something. So I will get the numbering wrong, but pi i's are 0 on suitable, on all x on some suitable h 2d minus I, right, 2d minus j's. So I think it should be 2d minus I, it should be non-zero, and the others should be 0, but anyway, okay, something. Right. So the idea is that this diagonal decomposition will give this conjectures, but of course the problem is in general we don't know the diagonal decomposition, but it has been written down in the case when x is a curve, when x is a surface, it has been written down. Okay, but and x is an abelian variety, so there are some examples where it has been, such a decomposition has been given. Yeah, so maybe I'll stop and I'll take questions. I don't have, I'm a little bit at loss what to say at this point. Yeah, so the ECM is a construction. It's a universal construction which was given by Nori. Okay, from given the cohomology and taking the values, it's a category, linear algebra construction. I have some notes on this, and there it's ECM, sorry? ECM stands for effective cohomological motives, and its construction is, you can see online notes. There are notes which I have gave in WashU 2 years ago, which are on AMS open notes. That gives one construction, one exposition. It's not as complete as what is there also by Nori himself, which was written by Nazmuddin as a tech file. That is essentially a sketch. And then there is a detailed write-up by Annette Huber and Stefan Müller-Stark, and which is more or less what I followed while giving the lectures, but then I found some slight gaps, and so I have to correct some of the things. So these are 3 places where it is. It's called periods and Nori motives. Okay. And so these are the 3 ones, but I think there are later other ones. I think Arapura has some write-up on some of these things and so on. So unfortunately, yeah, you have to search through various sources and find it. Okay.
One answer to one question Nitin asked about the example. Take a smooth affine surface in 3 specs. Projective closure is also smooth. I guess such a surface is simply correct. Take a smooth hyperplane section of lambda. So x comma y has the property that h2 is free again and everything else is 0.
Okay, so Srinivas is saying is taken a fine surface in A3, smooth.
Yeah, that's that x bar is also smooth in P3.
Yeah. So x bar is smooth. And then take a curve with it.
Another smooth hyperplane.
Then xc is.
So I claim H2 of this is free abelian. So I've done my combination correctly. And everything else is free. The reasoning is that X is affine.
Right.
So the Artin vanishing or whatever condition.
Right, says that it has only cohomologies.
Only in degrees 0, 1 and 2. So space X is there.
Right.
And H1 is 0. Hopefully.
By the way, that's a consequence of basic lemma. No, I'm just saying that's a consequence of basic lemma also in this case.
No. Basic lemma is, the point is your Z is also given.
Yeah.
I'm not
No.
going to choose any code.
I'm understanding. I mean, yeah. In this
Some of that extra.
yeah. So
Okay.
hi
Give me example.
xc is 0 anyway for. So what Srinivas remark is that is 0 for I greater than 2 in any case. And then you have to check for I equal to 1 and 0. Okay.
I'll just be careful. My impression is might be 2 in any direction. But the extra is the red. You're already given a subroutine where it is fixed and your y has to or whatever from y. And your z has to contain. That's not obvious.
Yeah. Yeah, in this setup. Yeah. Yeah, I suppose you're right. So if I remember correctly, if you take something like a smooth projective variety, take a ample divisor which is part of a divisor with normal crossings, take x minus the ample divisor and take the rest of the divisor with normal crossings. I think that x minus a comma, then it's an example, I think. I'll have to check it, but so suppose you take x bar and you take a divisor with normal crossings, which is a plus b plus something, okay, where a and b are ample. And now you look at.
Take 2 of them. A plus b.
You can simply take 2 of them. That's the simplest thing. I think here you take x bar minus a relative to d minus a. I think that's such a pair. Okay, everything's smooth. I think this is. Maybe.
At the integral level also this works. That's why I was a little careful.
Okay.
Free abelian.
Okay.
With Q coefficient, I think.
Q coefficients. Yeah. I was thinking in terms of Q coefficients. So this is b minus a.
I do remember Father does say the example of this type.
Yeah. This is okay. This one is okay. A and B ample, both of them ample. So on the other side, you can, this is a game you can play. There are a lot of situations where you can produce a y. Well, here you're going to do Hodge theory, so it doesn't really matter, you can take C coefficients. There are a lot of situations where you can produce a map, a y, a subvariety of x, in which this is an isomorphism. Or what we really want, which is that there's nothing on this side beyond a certain weight. Okay, and that is, in other words, you are trying to prove that a certain x comma y pair has no other terms in the mixed Hodge structure. Okay, so this has no PQ part in the right degrees. Okay, so there are a lot of such pairs, and therefore, after producing such a pair, you can ask if certain Chow groups are 0. Okay, so and you can try to prove. So it leads to questions of that kind. Whether you, so as I said, where, so if this is surjective, or at least surjective onto the part which is of positive width or whatever, then raises questions about triviality of cycles. So it amounts to, and that's where the diagonal decomposition plays a role. It is essentially says that cycles on X can be pushed up to torsion to be cycles sitting on Y. Okay. So because those groups are governed by these groups, so therefore that means that if I have a variety X where in certain range of cohomologies, the cohomology of X is the same as the cohomology of Y, where Y is a subscheme, then you expect that the cycles sitting on X actually can be pushed into Y by these conjectures. And then you could ask, can you prove it? Okay, so there are many such examples which one can look at. So a typical example is this kind, where you are looking at a hypersurface in a surface, and Lefschetz theorem gives you this. Okay, and so you can ask if the Chow group of a hypersurface is the same as the Chow group of the ambient space. Right, so hyperplane, ample hyperplane section. So, for example, so that would be in the classical setup. That's the Lefschetz theorem, which is, or the Grothendieck-Lefschetz theorem for codimension 1 cycles. But already for codimension 2, it's a non-trivial question, right? Because in particular, I suppose maybe Bloch's conjecture will come out of it. So one thing which I must say, I mean, just from the point of view of what kind of mathematical problems you want to study, it seems to me that in the theory of cycles, there are, after reading something like Fulton, there are two divergent streams. One is this kind of study, which is in some sense abstract and talks more about topology. And the other one is the kind of things which Fulton, with Eisenberg's book, talks about, 3264 and all that, trying to get various kind of interesting numerical and combinatorial identities associated with intersection numbers, calculate how many conics are tangent to 5 conics and things like that. What is Chazel's problem? And there are problems like that, and they are non-trivial because there's excess intersection. Okay, but ultimately then you're trying to make sense of calculating some numbers, and somehow that's a very different kind of question on cycles than this kind of question, which is about specific surface, where, I mean, because we are looking at cycles whose homology classes are 0, there is no number as such to be calculated. But
well, in the direction of those Fulton types in what was like computing numbers, I guess there are also questions of the type where you have infinitely many such calculations of sequences.
Can I make
the coefficients, you put them in some of the
series?
The series start having this.
Yeah, so there's a recurrence formula. Yeah.
No, I think it's a modular form.
Right. No, but that comes.
Good explanation, is it?
No, so in those situations, one of the simplest things is if there's a recurrence relation, then it satisfies the differential equation. Yeah. So it depends on the recurrence relation. That would mean that function satisfies a differential equation.
So
what does that difference?
Are going to come from other part of mathematics, and the knowledge of that is going to tell you what is.
Which one?
When you are calculating such numbers.
Right.
For examples which come from some other part of mathematics.
More, I mean, I would say that quite often group theory.
Give such numbers, really
yeah. So the question, I think.
What is the road? Right, the series have changed a modular form.
For example. And nobody knows why, right? I mean, in some sense, nobody knows exact connections. Right. Well, physicists claim they know why. Yeah. But in general, yeah, so you'll get some function, and it very often turns out that combinatorially described function has some other combinatorial or multiplicative properties and so on. But then you can ask, okay, you got this function, it appears in intersection theory. Why does it appear in intersection theory? What does it have to do with the original variety? And the physicists have some. So these are the two types of questions which, that's a very, I would say that's in some sense a different type of question to this kind of question. At least I have not seen anyone connecting these two. People either work in this or in that. Maybe the Russians work in all of them. So. So that is beyond me because I don't know all those spaces. Perfect type.
There are people who work.
So people have certainly done chow groups or stacks and things like that. Okay, so I'm sorry today it was a bit of a mess, but I was trying to organize the notes and in the process I forgot some of the things. And I wanted to get to the point which Sudarshan wanted to hear. Where does the connectivity theorem come in the picture? Okay.
So let's start